Good evening. My name is Charles Anderson. I'm the president of Augsburg College, and part of the tasks assigned me include welcoming individuals and groups. Sometimes I pass that responsibility off to staff, frankly, but I have never done that for the Sverdrup Visiting Scientist Lecture. And I think if you haven't been here before for one of these, you will understand why this is a must event for me each spring. This is the 6th annual lecture in the Sverdrup Visiting Scientist program. It is a time to reflect on the wonders of the universe and our place in it, a time when one's horizons are pushed back to infinity. We have some main players tonight. I'm not going to spend a lot of time on them because information is given in your bulletin, but one group of players is the Augsburg College Physics Department. Since the founding of the major in 1959, over 140 physics majors have graduated. Some go into business careers or into high school teaching, but the great majority have moved on to earn advanced degrees in physics and related fields. They represent one set of players. The second is an individual without whose beneficence, if you will, his kindness and interest, we would not be here at all. In 1990, this person established a program in honor of his father, General Leif Sverdrup. General Sverdrup graduated from this school in 1918. He was noted as a distinguished alumnus in 1958. And in memory of his father, Johann Sverdrup of St. Louis has established this program. This is the 6th year, and he also assists the physics department in many other ways. And I don't know if you want to stand, Johann, or just raise your hand, but we're delighted that you could come to the program. Thank you. Another group of players are the participants in the Minnesota Space Grant Consortium. You can read about that in your brochure also. In 1991, a number of schools received a 4-year grant from NASA with the University of Minnesota, Bemidji State University, and Augsburg College. The goals of the consortium was to help develop the next generation of scientists, and they have particular emphasis upon the place of women, underserved minorities, and persons with disabilities in the study of science and preparation for careers in those particular fields. They are concerned also with K-12 education, and I'm sure the majority of the people here tonight are related in one way or another to the outreach programs of the Minnesota Space Grant Consortium. You are especially welcome. And the main player, at last, is a person with degrees from the University of Texas, from Harvard, and most recently a PhD in astrophysics from Columbia University, which he received in 1991. For several years, he has divided his time between being acting director at the American Museum Hayden Planetarium in New York City and a lecturer and researcher in Princeton University's Department of Astrophysical Scientists. He is a writer, co-authored many articles, and as well as 2 books. It was of interest to me. One is called Merlin's Tour of the Universe, has been translated into Spanish and Japanese. I will not tell you all of the societies to which he belongs. I will mention that as of May 1st, he will no longer be the acting director of this, I think, most prestigious planetarium in the United States, but he will be the director and holding an endowed position, which is better still. I'm very pleased to present our speaker, Dr. Neil deGrasse Tyson.
Thank you. Thank you very much. It's indeed an honor and a pleasure Like anyone from back east, I had these fears of coming to Minnesota in a month other than July. But I spoke with people on the airplane and they said things are just fine on my way over. I want to personally thank Johan Sverdrup for providing the resources to make all of this possible. I think it's a wonderful program, and it brings a flow of ideas, of late-breaking research, and all the places I've ever seen people do that, it's infused the community with a sense of excitement. And so I honor you for this effort. And today I'm going to basically tell you how to get killed in a black hole. Now I have a combination of slides and overheads. We'll see what works best. In fact, for every overhead I have a slide, but we'll see what works best here. That doesn't work too well, so we might go to slides, but this is just my first overhead here. So my title is simply Death by Black Hole. I don't know how well people on the far edges can see. I'll be doing a lot of hand waving of what it is, so maybe that can work for you. This is just the front, the first overhead. Death by black hole. And actually, could I have just slightly more lights than this? If you crank up the rheostat just a little bit. A little bit more. Okay, that's good. I think you can still see this just as well. And I just don't want to trip on anything here. That's fine. So, why bother to learn how to die in a black hole? Well, actually, this is a first step to understanding how devastating black holes can be in nature. Because, yes, if you fell into a black hole, you would die a spectacular death, but things fall into black holes all the time that aren't people, like stars, like whole clusters of stars. And when this happens, it's quite spectacular. And so once you learn how a black hole will kill a human being, you'll have deep insight as to how it actually kills a star. So let's see if we can go to the first slide. And I'm told I have a very long control button here. Oh, okay. Forward. Good. Can I have a little bit more light as well, again? I'll be gesticulating a lot, and so it's important for what I need to talk about. And you can still see this, right? Except for those at 130 degrees over here. So the question is, how will a black hole kill a person, a star, or a star cluster? And that's what you're going to learn in the next 40 minutes as I get comfortable. If you don't mind. Sir, you don't mind if I just want to do that with permission. I'm not very good at drawing realistic figures, so my stick man is the best you're going to get for this lecture here. But I gave him a hat just to make him a little more personable. So let's see. To understand that, how a black hole will kill a person, we've got to, first things first. So what is a black hole? And it's very simple. In fact, for something as profound as black holes, it has one of the most simplest explanations for what one is of any object I could ever describe to you. So it's a pleasure to describe to you how a black hole works compared with a rotating pulsar, okay? Black holes require you to understand the notion of escape velocity, and that's pretty simple. On Earth, there's an escape velocity of 7 miles per second. And what does that mean? Well, do you remember when you were growing up and your grandparents passing on among the many adages that they had in their stockpile? One of them was, what goes up must come down? Well, that's a lie. Well, it's not a lie. They weren't lying to you as much as they were misinformed. Okay? What goes up must come down is a consequence of how weak we are and how weak our throwing arms are. But I could take something like my shoe. Let's try this. Like my shoe, and if I give it a certain speed, let's say a couple miles an hour, it'll go up and then come back. Fine. If I throw it faster, it goes higher before it comes back. And I can keep throwing it faster and faster and faster, and it'll go higher and higher and higher before it comes back. There is a speed that I can throw my shoe or anything else where it'll leave this Earth so fast that all Earth's attempts to try to slow it down will not succeed, and it'll escape Earth forever. Forever. And that speed is the escape velocity for the surface of the Earth. And that value is about 7 miles per second. So I'd have to throw my shoe 7 miles per second, and I can kiss it goodbye. It'll get to the edge of the universe. Okay? But I just bought these shoes, so I'm not going to do that. Okay? 7 miles per second. It ought to make sense that if Earth's gravity were stronger, that the escape velocity for Earth would be more than 7 miles per second, because you'd have more gravity to overcome. That might make sense. And the opposite would be true as well. If Earth had less gravity, perhaps it would require less of an escape velocity. Well, in fact, if you go to the moon, escape velocity from the surface of the moon is only 1.5 miles per second. You go to the sun, escape velocity is nearly 400 miles per second. So obviously the surface gravity on these three objects is very different, and of course, so is the escape velocity. By the way, if you're thinking that 7 miles per second is fast, it is fast, but in fact we've actually sent astronauts at this speed. The astronauts who went to the moon basically hit 7 miles per second to leave Earth orbit and go on their way to the moon. This is way back in the 60s and 70s when we went to the moon. Remember that? The Apollo program. But to do that, by the way, required the largest rockets ever to launch anything into orbit in the history of the space program, and that was the Saturn V rockets. The thrust on the Saturn V makes the space shuttle look like peanuts. And here was the Saturn V. I forgot, it was like 20, 30 stories tall. All of that was just fuel. Where were the astronauts? These little itty-bitty things at the top strapped onto 30 stories of fuel, just to get them off the surface of the Earth to the moon. In fact, most of the fuel was used just to get the rest of the fuel that hadn't burnt yet into orbit to ignite that fuel to get them to the moon. Did that sentence make sense? Yeah, I think I said that right. So getting off the surface of the Earth is a major challenge, a major energy problem in space travel. And in fact, that's why a lot of people want to build spacecrafts from a base that has much lighter gravity, like the moon or even in an orbit. Like out in one of these special points where gravity balances between Earth and the moon. And then if you're there, you can just sort of toss all your raw materials and then build a very big spacecraft, and that can take you to wherever you want to go. So at the moment, that's stuff of science fiction. But if we ever want to go any place other than the moon, that's what it's going to take. So here we have escape velocity. So depending on what kind of object we're talking about, the escape velocity can be higher and higher and higher and higher. Now for each of those objects, just to show you that we just don't make this stuff up in our head, there are equations where you can calculate escape velocity. I was told there are a couple of physics majors in the audience here. Raise your hand if you're a physics person. There's one, 3 others admitting it, yes, okay. Anyhow, this is one of the simpler equations of gravity. But anyhow, there's an equation here where you can compute the escape velocity. These are all variables here except for, but the 2 things I want to call to your attention, there's an m in the equation for the mass of the object, and there's a radius in the equation. If you change either one of those, you can influence the escape velocity of an object. So both mass and radius affect this. I'm going to tip this just a little bit because I think, is that a little better over there? Okay. And you guys can still see it over there, right? Just to be a little fairer to them. Both mass and radius influence the calculation of an escape velocity. And that's important to know. Because if Earth somehow became more compactified, didn't change its mass, just squeeze it. The mass doesn't change. These two are constants, don't worry about those. The radius of the Earth would drop. And if you remember your algebra, a small radius, a small denominator gives you a big number at the end. So you can increase the escape velocity just by shrinking Earth. Well, with the escape velocity business, what happens when you get to an object that has such a high escape velocity that the escape velocity is greater than the speed of light? What is the speed of light? It's basically about 186,000 miles per second. Actually, speed of light has an exact value. In case you're wondering, it's exactly 299,792,458 kilometers per second exactly. The speed of light is now a defined constant. It is no longer subject to experimental error. There are some cogent reasons for that decision, but suffice it to say that it has been done. What this means is if one day we'd measure a different speed for the speed of light, add a few decimal places here, you know what that'll mean? Because this number's not going to change, I'll tell you that right now. If you get other numbers here, guess what happens? We redefine the length of the kilometer. I kid you not. More precisely, we redefine, I have the units here wrong. This should be meters per second, not kilometers. So we redefine the length of the meter to account for that difference. So one day you might wake up a little taller than you thought. It's for that reason. Anyhow, so light is the fastest stuff in the universe. That's a really fast speed there, 186,000 miles per second. And so if the escape velocity reaches 186,000 miles per second, light can't get out. And light is the fastest stuff in the universe. So that means if you fell in, you're not coming out either. So you don't come out, light doesn't come out. If light doesn't come out, it's black. If you fall in, don't come out, it's like you fell into a hole. So what shall we call these things? Black holes, thank you. And in my profession, in the field of astrophysics, like baseball umpires, we call them as we see them. Okay? Out in the universe, there are big, bulbous red stars, we call them red giants. There's small white stars, we call them white dwarfs. Stars that pulse, we call them pulsars. Okay? The universe is complicated enough without trying to derive some fancy Latin or Greek root word to complicate things. Do you hear that, chemists and biologists? Okay. Honestly, I try to read some of these biology articles, and every next chemical thing is like bigger than the next one. And it's like a test. Not only can you pronounce it, but can you remember how to pronounce it? And we give you such cool words for stuff in the universe. Quasars and black holes, and the galaxy has a spiral shape. It's called a spiral galaxy. Anyhow, where was I before you took me off track here? So there you have a black hole. Now it's not black here. It's already about to be a black hole. And now some exotic things happen in the vicinity of a black hole. And it dates back to Albert Einstein in 1916. He actually wrote this out in 1915, but it wasn't published until 1916. And in it, what he described for gravity was that gravity wasn't a force the way you normally think of forces. It wasn't just action at a distance. Gravity, he imagined, was the response of matter to the shape of space and time. So that if you go out into space and time and somehow warp it, and then you send a projectile through there, it will bank a turn around the presence of that matter that's warping the space. In Einstein's conception of gravity, that's how you describe gravity. And so in that picture, I've got three, imagine gravity as this big rubber sheet, and you can take your finger and poke it, but the effect of the effect of poking the sheet it's as though you're putting a mass sight there. And the deeper you poke it, the higher that mass is. And so what I have here, imagine this is the curvature of space in the vicinity of Earth, and then the curvature of space in the vicinity of the Sun. Notice how that curvature is much deeper. And then you have here the curvature of space in the vicinity of a black hole. And now you can viscerally identify with the challenge required to get out of the gravitational pull of a black hole. What you have to do is climb out of this hole. And this hole is conceptually relayed by how deep this dimple goes. Now, in fact, what's not exactly representative about this is that this is a hole in just 2 dimensions, when in fact, in a real black hole, you can fall in any direction. It's not like a hole in the street where you can only fall in going that way. In this black holes, you can fall in no matter which way you fall. So this is one of the basic principles of Einstein's general theory of relativity, published in 1916. And every prediction that comes out of that theory has shown to be correct. It's amazing. The guy was in touch with the universe. So he's as famous as he deserves to be. In fact, he did probably 7 Nobel Prizes worth of physics. You just go down the list. They gave him a Nobel Prize for something much less profound than his relativity theories, but he still got one. But really, if you split up his work and dished it out to 7 people, 7 different people would have gotten a Nobel Prize. So he was a smart guy. Right, so notice here, however, that this is what happens to gravity. Now, I haven't told you how you die yet, because so what if it's high gravity? You just fall in a little faster. It's like, so what? Well, the fact is, it's not just the gravity that gets you. It's something called tidal forces, which is not simply the gravity on your body, it's the difference in gravity between your feet and your head. That's what'll get you. And what have I drawn here? I've drawn a little stick man with his top hat, and I just want to convey to you the fact that here we are standing on Earth. I'm standing here, and the force of gravity relates to how far away you are from the center of that source of gravity. So right now, my feet are closer to the center of the Earth than my head is. So my feet feel a stronger force of gravity than my head does. Pure and simple. By the way, that difference is not very much. Otherwise, you know, we would. So this goes unnoticed by normal measuring devices like your body. But what you can do is you can calculate what the difference in force is between your head and your feet. You calculate it. And then stick your body in different gravitational scenarios and see what happens. But that difference in the force of gravity is known as the tidal force. Why? How did it get this name? Because it's that phenomenon that gives us tides on Earth. Let's see what that looks like. Here we go. We've got the Earth-Moon system. Let's imagine Earth, a moonless Earth right now. You geologists, this is just a schematic here, okay? There's not Noah's flood here with the ocean all over the Earth there. Imagine an ocean layer all over Earth. uniformly spread. But now we stick the moon in the way. We got the moon here. The moon is tugging on Earth. The moon's got, it's got gravity too. So here we have the right side of Earth is closer to the moon than the left side of the Earth. So this side of the Earth is getting pulled in closer than the back side of the Earth. Now, by the way, this happens in the solid Earth as well as the liquid part of the Earth, the oceans. But it's much more noticeable in the oceans. So, land masses actually rise and fall by this effect. You don't notice it, though, because everything moves with it. Whereas oceans that comes in, tides come in and out. So this is what goes on. And we have a stronger moon gravity on the front edge and a weaker one, and it stretches it. It's very simple. Stretches it. Now, I've been asked by many people, I write this column for a magazine. It's a question and answer column. And it's a question and answer column on the universe. And I occasionally get questions about tides, people saying, well, tides are at a maximum during full moon. We all know this. And people say, well, could it be that the tides and the full moon, and if it affects water on Earth, and the human body is, 80% water, so then maybe the tides affect the human body, and then gives you a whole population of lunatics during the full moon phase. Okay, this moon behavior during the full moon, and all the cops report that people are behaving strangely. Well, let's figure this one out. All right? It is true, your body's mostly water. It is true, tides from the moon are influencing the oceans on Earth, and the oceans are made of water. This is all true. I got no problems with that. But what you have to ask yourself is, what is the difference in gravity from one side of your head to the other compared to the distance to the moon? That's the tidal force of the moon on your head. Okay? Now, if you did this, okay, if your head were 8,000 miles across, just like the diameter there, it would stretch your head. Yes, and that would be bad, all right? It would have untold consequences on your mental faculties. But your head is not 8,000 miles across. If you got a big head, it might be 7 inches across. Let's calculate it. I've done that for you, save you the effort. That way you don't have to do it when you go home tonight. I calculated the difference in moon's gravity from one side of my head to the other side of my head. And guess what? I'm not going to tell you how much that is, because it's a meaninglessly small number, but I'm going to compare it to something else. We all go to sleep with pillows on the bed, presumably, okay? If you have a down pillow, and you're one of these people who sleeps with your head under the pillow rather than above the pillow, some people do that. They cover the head, particularly if you have noisy neighbors. Then the force of the pillow on your head is 10 trillion times larger than the tidal force of the moon on your head. And I don't see anybody writing stories about the effects of pillows on people's heads. But they're writing about moons on people's heads. I should write science fiction and do it with the pillows. See what people... Blame the pillow. All right, so anyway, I just want to get that straight here, okay? Now let's get back to the black hole. All right, so tidal forces will stretch things. Now let's see what effect that has. Here's our stick man again. Again, at all times we're comparing the force of gravity between your feet and your head. On Earth, I'm 6 feet tall. There's only a 6-foot difference, yet the radius of Earth is about 4,000 miles. So that's not a very big difference. But black holes can get very small. So small that your height can be significant compared to the distance that you're about to fall. It could be significant. And so as you begin to fall, look at this, your feet are twice again as close to the black hole as the top of your hat. So your feet will begin to accelerate towards the black hole at a different, higher speed than your head. Now, humans, you can stretch an inch or two, okay? With the right apparatus, we can get you an inch taller, inch and a half maybe. But there's a limit. You know, you're made of bones and tissue and flesh. You're not made of titanium, all right? So I've drawn a little stick man here actually stretching, but clearly that's not what would happen because we are not made of rubber. We will not stretch, except for that inch and a half maybe. What will actually happen is your body will systematically snap into pieces, okay? As your feet leave your head, you'll first snap in the middle. Then your upper half, that then gets to feel a strong tidal force. You'll snap there as well. So in effect, you will bifurcate in pairs. So after the first split, you're in 2 parts. After the second split, you're in 4 parts, then 8 parts, then 16 parts, then 32 parts, and this continues, doubling. 64, 128, 256, 512, 1024, 2048, 5096, 4000, did I say that? Whatever that double that is, and that's a lot of pieces to find yourself. And so I've tried to draw that here. And here's a little stick man face here. And it just breaks into pieces. Poor fellow. Now, what's cool about this is in half of my capacity, I do astrophysics research at Princeton, at the university, and I spend about 3/4 of my time there, and the other 3/4 of my time I spend at the Hayden Planetarium, where I write sky shows. And the sky show that I wrote about 8 months ago included a scene where we tossed somebody into a black hole. Now, the way you can get away with doing this is you just do it on a computer. You get someone to pose for a few photos, and then you just sort of morph them on the computer, and you can make anything happen that you want. So what I have here are some of the original preparation slides that went into this sequence of scenes. And some of the matting is off because we actually mat it specifically for a dome. But I'll show you what that looked like. Actually, this is a crack in the slide, so ignore that. What we're going to do is we're going to toss somebody into the cone, this funnel warped space of a black hole. We're going to toss somebody into that. This is a laser image projected on the dome of the Sky Theater. Okay? So we took one of our interns. Here she goes. All right, now she gets masked perfectly on a dome. This is one of the early slides that we used to test the concept. But here she is, happily floating there in space. Okay, just thinking like everything's just fine and dandy. Not knowing that there's a secret hidden black hole that she's floating towards. So as this begins to happen, she begins her descent into the black hole. And there she is, about to fall. Then we thought we'd have a little fun. She's about 4'11", so we thought we'd stretch her like 8 inches before we really messed with her body here. So we decided to stretch her a little bit, and this made her only about 5'6". But then we said, okay, it's time for action. And so, in this sequence, by the way, that cone is like rotating, and we have really threatening music going on in the dome at the time. So all the little children burst out in tears and things. It's terrible. We encourage them to go to the kids' shows, but they like to see the adult show, so that's fine. But this is actually what would happen. And here she goes, grimacing in pain, as we broke her up into tiny pieces. And then, of course, there she goes, never to be seen again or heard again by anybody in this universe. And her name is Amy Gallagher. She's our assistant producer, so she volunteered for this computer experiment. So with this, let me just back up to that. So the point of this exercise is to show you that if you have a competition of forces, and one force is constantly getting greater and greater and greater, eventually it wins out. You had some experience with this. If you sit in a chair every day, to eat dinner, and you sit in a chair again, you just rely on the fact that the chair will always hold you up. That's basically a competition of forces. Your weight against the ability of the chair to support your weight. Now, if you've been eating too much, you gain in weight, one day the chair cannot support that force, the chair breaks, and you fall. And that's just, you do this in intro physics, what one force against another would have to say. So, onward to the universe, what black holes do in the universe. What I have here are 4 scenes. These are like 4 scenes in a play. The first scene is up here, the second scene is there, third, and then fourth. You might ask, if a black hole doesn't give you any light, how do you know it's there? Basically, you don't. So you have to find ways that might be useful to find out if it's there. And one way to do it, which came out right when black holes were first on the map, is you look into the sky for binary stars. By the way, you look up in the nighttime sky tonight, you look out there, most stars you'll see are at least star pairs. Some are triple star systems, others are quadruple star systems. In fact, single star systems are relatively uncommon as a place for stars to exist. So this is not an exotic suggestion to say, let's consider a binary star system. By the way, just a tidbit, you know the closest star to the sun? Anybody know what that is? Alpha Centauri. I bet you didn't know, or maybe you did know. Alpha Centauri is not a single star. It's a triple star system. So in fact, it's the Alpha Centauri system. In that system, one of those stars is closest to us. That one has a name, all unto itself, and it's called Proxima Centauri. That's the near one. Okay? A little tidbit. Cosmic tidbit. That'll make you popular at cocktail parties, you can recite these things. Anyhow, so we start out with a binary star system, and we let one of them become a black hole. It does what it does. It's a black hole. It's sitting there minding its own business. Now the second star then goes through an evolutionary phase, these big red things, which we call red giants. And I don't think you appreciate how big a red giant is, so I'm going to tell you. The sun will become a red giant. If you hang around, you need to wait about 5 billion years. Okay? Billion years. When it does, the outer shell will begin to expand, and it will engulf the orbit of Mercury. And it will continue to expand until it engulfs the orbit of Venus. And it'll continue to expand, and it will engulf the orbit of Earth. So 5 billion years from now, you'll see the sun in the sky just get bigger and bigger and bigger until it is the sky. And then Earth is this charred ember orbiting deep within the sun's surface. And our oceans would have long evaporated. And our atmosphere would be long gone. And so occasions to, you might have wanted to visit further out planets by then. So it'd be nice to have a healthy space program when that happens. Take the next bus out. So it becomes a red giant, but red giants become so big that they start getting loosely attached to their material. And they can actually cross the border between it being attached to the red giant and attached to the black hole. And so the material can be stripped off and spiraled down into the black hole, toilet bowl style. It's exactly what it looks like, a toilet bowl. There's an official term for it, accretion disk. Accretion as in something that accretes. And I have some colleagues of mine who study accretion disks, and he's put on some weight, recently, so anytime he talks about accretion disk, he pats his stomach. Here's my accretion disk right here, patting his growing stomach. So there are a lot of sort of stomach jokes in the field. But anyhow, as this material spirals in, I'll tell you what it does. All the gas wants to get to the center of the black hole all at once, but it does not succeed in accomplishing this. As it comes down, it starts to swirl around the black hole, and the gas that's closer swirls around faster than the gas that's farther out. It's just the toilet bowl effect that I was describing to you. Well, this sliding creates friction because the whole disk isn't moving as a solid piece. It's shearing, and that creates friction. So much friction that the disk gets hotter and hotter and hotter and hotter and hotter, and it starts glowing. It starts glowing so hot it emits X-rays. That's how hot it glows. Now, just an aside, you've heard of things that are red hot before? Your stove, you put it on, if you have an electric stove, it gets red hot. Red hot is the coolest of all glowing hots. If you could crank your knob higher on the stove, they don't let you do this, the stove manufacturers. If you can crank your knob higher, it will start glowing white hot. Crank it higher still, it'll start glowing blue hot. Crank it higher still, it'll still be glowing blue, but then it'll start giving off X-rays. Then you'd want to go into the next room when that happened. But this is way hotter than you ever need to cook your food, so stove manufacturers don't bother. But in everyday life, you think of red hot as hot, but I think of the universe every day, and to me, blue hot is hot. So, I'm about to beg for sympathy because when I come out of my office and I walk up to the water cooler in the corridor, and there are two spigots. One has a red cap on it, and the other one has a blue cap. And I'm sitting there. I have to remind myself, okay, I just walked out of my office, so I've left the universe, and now I'm in the real world where people think that if it's red hot, it's hotter than blue hot, and I don't know how much of my life I've wasted staring at a faucet, okay? I swear to you. And I have to like rethink it. What would an artist think? They make things red as hot. So, let it be known that in the universe, if you see something glowing blue hot, it's way hotter than something that's glowing red hot. So, the point is this material spirals down, and it wants to radiate so profusely. It wants to just radiate. That what happens is it can't radiate in the disk because the disk's in the way. So these jets start sticking out. Material, before it ever gets near the black hole, it's trying to get in there, bam! Energy kicks in, jets spew out above and below the black hole. Above and below. So not only are X-rays a signature of a black hole in this kind of cosmic dance, but also jets, jet phenomenon. And I've got, I think, a picture, an artist's rendition. The third one here will show a jet. This was used for the poster, I think. Is that right? This is like one of the way coolest pictures of a black hole ever drawn. It was drawn by the staff artist at the Hayden Planetarium in the early 1970s. This one. The staff artist. And staff artists at the planetarium, they've got to know some science. Otherwise, they're pretty useless to us. So they anchor their visions in what is known about science. And in here, he tried to convey the fact that a black hole is a hole in all three dimensions of space. But he captured one of them with these, one slice through those three dimensions in this plane, and he shows things falling in. And way down at the bottom, he has a red giant star with some material getting flayed off its equator. So this is actually a very famous painting. It appeared on the cover of many magazines and books. And from my research, it is the very first artist's rendition of a black hole ever painted. And this was done in 1971. Our current planetarium artist, painted this next one. This one is one that does not have jets, but it does show the heating up of the gas. And you get a sense of the shearing effect, because some places you have hotter regions than others. But so you can get some texture in there with different temperatures. But by and large, you get the sense of the spiraling falling down into the central abyss. Now, if the influx of material is high enough, that's when you get the material has to come out somehow, and there it goes. So deep down inside here is a black hole you don't even see. And all this material is trying to get into that one spot, and it can't do it all at once. Friction heats it up, it begins to radiate, and jets spew out above and below. And such is the signature. And so, by the way, we see jets. We got pictures of these things. Okay? You look in the centers of galaxies, there are jets spewing out. Millions of light years into space. Jets. So let's see. These black holes I just described to you are actually your black hole that you get when a star dies. A star much more massive. The sun will not become a black hole. Don't worry about that. But there are other kinds of black holes that we find lurking in the centers of galaxies. And these black holes I'm calling monster black holes because they are big. They are monstrosities. I'm talking about black holes that have 1 million times the mass of the sun. 1 million times the mass of the sun. Where do we find them? No, they're not just wandering around space. They're lurking deep in galaxy centers. And before I describe the black hole to you, eating a red giant, it's a very nice process. It'll, take a few million years to eat off the outer layers of the red giant. It's taking its time. These black holes can eat a star a day. Gobbles it up. Star a day. And you can calculate how much energy would be coming out versus how much gets lost into the black hole. And you find out that that energy, we are convinced, is the source of energy that powers quasars. And quasars are these mind-bogglingly luminous, mind-twistingly small, mind-expandingly distant objects in the universe. We think a quasar is an ordinary galaxy that has extraordinary things happening in its core. And we think it's got one of these monster black holes dining upon stars that wander too close. Now, why do we believe this? Because, first of all, quasars were discovered before black holes were on the table. We looked in the distant universe. There's an object, looks like a star. It's giving off radio waves, but stars don't give off radio waves. So it's quasi-stellar radio source. Hey, there's a word in that. Quasars. Okay, now, that's the origin of the word quasar. It didn't start out as the name of a TV set, okay? Just, so in that, later on, black holes were discovered, but we found out that these quasars had to be very small. There are cogent reasons to believe that quasars are small, no bigger than maybe a couple of light years across, maximum. Yet they're outshining entire galaxies. A quasar might be 1,000 times the luminosity of our whole galaxy, crammed into a space the size of the head of a pin, a galactic pin. So, crammed into the distance between here and the nearest star. 1,000 times more luminous than the entire galaxy. So when black holes came on the scene, people raised an eyebrow and said, maybe this is a way we can get a lot of energy coming out of a small volume and stick it in the middle of these galaxies. And in fact, that is the prevailing model for what you get as a quasar. Bright, small volume, exotic energetics. And right down in the center of a galaxy is where you would find it. Your monster black holes. Now, think about this. Quasars, we only see them in the very distant universe. We don't see them nearby. And when you look out in the universe, you see things not as they are, but as they used to be. Because it took light time to get here. So, for example, when I see you, right now, we're looking at each other, and we're thinking, well, this is happening right now. No, it already happened. How long ago? About 20 nanoseconds ago. That's not very long, so we treat it as being instantaneous. But the nearest large galaxy to us, the Andromeda Galaxy, it's 2 million light years away. 2 million. We see it as it was 2 million years ago. They see us as we were 2 million years ago. We've got a galaxy called M100 that's 65 million light years away. It took its light 65 million years to get here. It took our light 65 million years to get to them. Now, what happened 65 million years ago? If you look at the fossil record, somebody became way extinct 65 million years ago, our friendly dinosaurs with the big teeth. On that galaxy, if they had super duper high-powered telescopes, they would be watching us, watching Earth with dinosaurs running around on it, looking worried as the comet approached. As you look to the outer universe, we see back in time, and these quasars represent an epoch of the history of the universe that it no longer exists. So if quasars have black holes, and black holes are a source of this energy, and there are no nearby quasars, that must mean the quasars somehow turn off between the beginning of the universe and now. Yes, they do turn off. Think about it. I'm a jumbo monster black hole. Stars are coming by, I'm just eating them up. Grabbing them, eating them. Eventually, I've eaten all the food on my plate. Okay? Any star that would have come by me has done it because I've eaten it already. And other stars that are far away, they're at a safe orbit. So the very process that makes quasars a quasar are the seeds of its own undoing. And so we have a mechanism for a quasar to exist and for a quasar to turn off. Now, if that's the case, that must mean that some of these nearby galaxies might have black holes in their center, fully evacuated space around them. And in fact, that's exactly what we find. We look to nearby galaxies, the list is growing, it's up to about 12 now, galaxies with black holes measured in their centers. How do we know there's a black hole there if it's not eating stars? There's another way to find out. And this is where the Hubble telescope comes into, becomes a very valuable instrument. Because if a black hole is there and a star comes near it, it feels a very strong gravity and it'll want to speed up as it whizzes by. At a safe distance, mind you. But it'll speed up as it comes by the black hole. And its speed tells us exactly how much mass was inside there. Very basic laws of gravity that tell us how to do this. And so the Hubble telescope enables us to see way down close into the center of the galaxy and look at the orbits of stars nearby. And just outside of the zone where it has a cleaned out dinner plate, we see stars whizzing at a speed that requires there to be a black hole in the center. So we got a galaxy with a 10 million solar mass black hole. And just so that, I don't want you to have black hole envy, the Milky Way galaxy, we think it has a black hole of about 100,000 solar masses. Much less than others, but we think one is there also. Here is a spiral galaxy. Not ours, but one that resembles ours greatly. We can't just get a bird's eye view of our galaxy because we're in it. It would be like an unborn child trying to photograph its mother. It's not something you can accomplish until you're born, and then you can look back and take the picture. So in this, I just want you to think about this. Deep down inside there, we believe there to be a black hole, long since dead of its quasar effects. But this galaxy has about 100 billion stars. So there are about as many stars in this galaxy as McDonald's has sold hamburgers. Okay? The last I checked, it was 99 billion. 99 billion. Which is a staggering thought, especially if you're a cow. But I show this because it's pretty and that it resembles our own galaxy, and it's got 100 billion stars. And this next picture, right from the Hubble Space Telescope, is known as the Hubble Deep Field. Maybe we can dim the lights just a little bit for this to get a better view. There's somebody on the light switch there. in this picture, it's a little grainy, sorry about that, but in this picture, except for two items on this picture, except for two things. You see a little sparkly thing there? You see another sparkly thing there? Those two objects are stars sitting on our nose as we look out of our galaxy into the vast universe beyond. Every other smudge in this photograph is a galaxy. An entire galaxy unto itself, each with its own assortment of 100 billion stars. As you go far enough back, more and more of these galaxies will have activity in their nucleus until you get to a point where quasars reign in the land, in the space. And in here, we see galaxies. If you look closely enough, there are galaxies that are actually interacting with each other, almost like a cosmic ballet, where the structures of the galaxies are twisted apart under the influence of each other's gravity. But I end with this picture just to share with you the fact that what inspires me to keep reaching out to the universe are pictures just like this, where I sit here and I gaze upon these spiral structures, knowing that perhaps we in the Milky Way are showing up in one of the pictures taken by some civilization on another galaxy there. And here we are looking back at each other, trying to figure each other out. The dimmest galaxy in this picture goes back 70 or 80% to the beginning of time itself. And so this is quite a sampling of the sky in an area, a patch about a tenth the size of the moon on the sky. That's what this picture is. 1/10 of the area of the moon in a field of view. And we believe this to be quite representative if we took that picture in any direction in the sky. In fact, it's been done, but not this well with Hubble. So I sort of like the fact that monster black holes are safely tucked away in the centers of galaxies. If you ever want to travel to another galaxy, just avoid the center. And for other galaxies that are you might encounter, basically, I only have one word of advice, and that's simply to avoid black holes. Thank you very much. Thank you. Thank you. Thank you very much. Thank you.
I'm interested in making two announcements. One, there are some microphones available, and Dr. Tyson has agreed to field some questions. We aren't going to go very long with open questions, but after a few minutes, then we'll have Dr. Tyson available to answer questions privately. Second, some posters have been provided. Youngsters can pick up a poster about black holes that away.
How young do you have to be?
During the refreshment time.
How young do you have to be?
We don't know. Youngsters, individuals who are thinking young, whatever, we only have, 100 or 200 of these posters. I'm afraid we don't have enough posters for the entire complement of the audience. But as many as possible, we want you to take home the memento about black holes. Do we have any questions? If so, please come to the microphones. I'll entertain questions. Yes, sir.
The fact that you find that quasars are a long ways away implies that they happened early in the formation of the universe.
Yes.
How do you think in terms of that much mass getting together that early in history?
One of the, you all heard the question, yes. One of the major challenges of modern cosmology is the fact that we see structure in the early universe sooner than the time available since the Big Bang would have permitted structure to form according to how we think structure forms. Okay? So that's currently one of the hotbeds of research. How can you assemble matter swiftly enough to account for such an early presence of fully functioning galactic process such as quasars? So right now it's a hotbed of research, and we don't have the full answer to that. They're forming earlier than we would have expected. And by the way, it's quite natural for there to be hotbeds of research where we don't know the answer, and that's a very natural circumstance for scientists to be in. Otherwise, you're not really working. If you're comfortably sitting within what is known, then you're not doing your job. You've got to find that edge, straddle it between what is known and what is unknown, and try to recover try to push forward our understanding of the universe. So, any other questions? Yeah.
I've kind of got one follow-up question to his and a little bit different question. What is the age of the oldest quasar that you've seen or that people have seen?
There will be surveys that will be conducted very soon, like in the next 4 years, that we expect to push the oldest quasar back even farther. But the current world record for a quasar is, in the jargon of the field, is at a redshift of nearly 5, which would put it, if you do the arithmetic right, somewhere between 93 and 96% backwards since from the present towards the beginning of time. So that's very long ago.
And then I'm a physics teacher, and I always get asked this question by my students, some of which are here today. And I don't know if there is an answer to this, but when stuff goes into a black hole, where does it go? So that may be a tough question, I realize. But
we can send you in and find out, but
yeah,
you're not
no
coming
thanks.
back. And I'm not going. Okay, once material crosses the boundary, that zone where the escape velocity is greater than the speed of light. By the way, we have a poetic term for that boundary, and it's called the event horizon. Is that cool? The event horizon. If you cross that event horizon, a few things take place. First of all, our equations show that all material crossing the event horizon will continue to collapse down to a single point, even though that point is much smaller than the size of the event horizon itself. Now, how can you fit all this matter into a single point? Sounds preposterous, and in fact, it probably is. What that means is our equations of physics do unusual, perhaps unphysical things when you try to collapse it down to a single point. So my response to you is to describe what's going on to matter as it approaches what's known as the singularity requires some other physics that we don't know about today. In the same way that Newton's theory of gravity, in the same way that Newton's theory of gravity did not apply under circumstances where your speed was very high compared with the speed of light. And so, yes, Newton's theories worked in a well-restricted case, but now you needed a deeper understanding of the universe to get to very high speeds. We still require a deeper understanding of the universe to get to that singularity, and one is not currently available to us. Now, that's the physics answer for you. The science fiction answer is you have left our universe, and possibly if this is a hole in space, you might connect to another part of the universe and pop out the other side. And in fact, in the early 1970s, people did some equations and you found out, well, first, you know, if I ask you what's 3 times 3, you'll tell me 9. You will tell me 9. Then I ask, well, what's the square root of 9? That answer is 3, but it's also minus 3, because minus 3 times minus 3 also equals 9. So the simple question, what is the square root of 9, has 2 perfectly legitimate answers, plus 3 and minus 3. Well, the equations for a black hole, turns out, have 2 legitimate mathematical answers. One of them gives you the black hole. The other one gives you the mathematical opposite of a black hole. Guess what that was called? A white hole on the other side. So people imagined that the black hole connected through a tunnel in space out to a white hole on the other side. So if you fell in, you'll get jettisoned through like one of these playground slides and pop out the other side. And what is a white hole? You can't get in it, stuff only comes out. Okay? Then what connects them? This branch, this conduit, that's the wormhole. So we have a black hole connected through a white hole, a wormhole to a white hole. And people suggested, well, if all sorts of energy comes out of a white hole, maybe quasars are these white holes tunneling through, coming out the edge of the universe, rather than invoking these exotic other descriptions. Well, you can calculate what a white hole ought to look like. And you can look at the spectrum, the qualities of the light, and what goes on in quasars doesn't resemble it at all. And so there's no evidence of a white hole anywhere in the universe. So right now it is paper speculation and food for science fiction writers.
So does that idea account for the theory that if you fall into a black hole, you have some limited ability to maybe move through time, since you can no longer move through space at your own?
Yeah, it turns out that if you have a rotating black hole and you fall in on certain trajectories, you can basically move through time in ways that wouldn't otherwise be possible. But they end up being very complicated solutions as you go through the fabric of space. And in fact, there are solutions where if you have like a cylindrical mass, it gets complicated, but if you have a cylindrical mass and you do a loop around that mass, and that mass is like very high gravity, you can actually come back earlier in time than when you left. Which is...
Okay.
Okay.
I have another question over here.
And it's by the way, it works on paper. No one's tried that in real life. And that's named in honor of a colleague of mine, J. Richard Gott, and it's known as a Gott time machine, which has legitimate solutions in Einstein's equations.
Okay, one additional question, and then we better break.
Okay.
You talked about would you call them jets that spurt out?
Jets, sure. Mm-hmm.
If a black hole is so powerful that it pulls everything in, and the jets are caused by friction, which build up enough heat to shoot the gases out, what happens to the gases after they've been shot? Do they circle back in, or?
No, in most of the cases, they've achieved escape velocity from that distance where they emanated. Okay, they're moving very, very fast, very high percentages of the speed of light. So it's gone. Now you can ask, well, how come the black hole really just didn't eat everything? And the only analogy I can draw to that is, I'm told, by the way, my wife is 5 months pregnant with our first kid. So this is something I haven't discovered yet, but I've seen it happen with others who have infants. Imagine the infant is a black hole, and you feed it stuff, but not everything stays down, okay? Some stuff comes shooting out, okay? Most of it will get eaten, some of it ends up on the floor, okay? So, in this same way, not everything gets into a black hole. Some gets shot out, and it has escape velocity for the black hole. And since he's standing there, I think we should get his question.
Okay, I have the next question, and then we'll stop.
I just wanted to ask about your feelings on the long-term, would you say, durability of the Big Bang Theory. In other words, there seem to be some people questioning it. Do you think that it will stand?
I have 100% confidence that it will stand for some very simple reasons. By the way, the people who, quote, oppose the Big Bang are very few in number, less than what you can count on a single hand. And so what's interesting is if an article on the Big Bang shows up in the newspapers, journalists, out of their journalistic ethic to always get the other side of a story, then seek out someone who opposes the Big Bang and then puts their rebuttal right next to it, as though the scientific community weighs both equally. Now this would be important in a political arena, because there are always different sides and nobody is right, just everybody's different. Whereas in the scientific arena, it is not respecting the actual scientific process that's unfolding. The Big Bang makes certain predictions about the universe that are indeed revealed. For example, it tells us how much helium there should be in the universe. It tells us that there should be background radiation, which was discovered in 1963 or 4. That was the famous microwave background radiation. The Nobel Prize was awarded for that. They're basic predictions of the Big Bang that are the pillars of that notion, that are consistent with what we see in the real universe. Now, if there are details that need to be worked out later, then that's fine, and that will happen. And there's still some problems that we're still working on. But simply because there are problems does not in and of itself mean that there's something wrong with the whole theory. And I'll give you a perfect example. In the days of Copernicus, back in the early 1500s, Copernicus is basically credited for restoring the notion that Earth orbits the sun, rather than the sun orbiting Earth. So he did this, and he said, well, this would be an easier way to describe what we see in the solar system. So he did this. You know something? He compared his predictions with what was actually going on in the sky, and they didn't match up. There were differences. So what do? Do we throw his whole notion out the window, or do we explore more deeply what's causing those differences? It was such a profound rethinking, and it was so valuable as a predictor of other things. The fact that Venus goes through phases. The fact, I mean, there were so many things it did explain so well that these few other things were relegated to details. And you know what those details were? Copernicus assumed that planets orbited in perfect circles. The notion of an ellipse was not fully appreciated at the time. That had to wait 40 years. And when people found out that planets actually orbited in ellipses, flattened circles, rather than perfect circles, all the errors in those measurements went away. So I submit to you that these basic tenets of the Big Bang theory are so powerful and so strong that what remains to be figured are actually small in comparison to what it predicts accurately. And there is no competing theory that predicts these pillars as accurately as the Big Bang. So I'm not saying that one day there won't be another theory about the universe. I'm telling you now that there is no trend in the evidence, in the current evidence, to alter our current understanding of how the universe was born in this Big Bang explosion. That's what the evidence points to. And it's, you know, I mean, some people are uncomfortable with it because it's like, that means the universe had a beginning, but how will it end? Will it be? And it's like, but science isn't about what makes you comfortable, it's about what's going on out there. That's what it is. And so that's where the Big Bang stands.
Okay, thank you very much. Can we have another hand for our speaker?
Thank you up there.